Okay, so we're finally going to get into some schematic design. This is like I said, a very introductory introduction. There's so much to learn with this. This is going to be just an intro to like how to do this and some key tips and tricks when you're doing your first schematic designs. So what is a schematic? A schematic represents the logical connections between components. So it represents nets connecting rather than the physical connection. So this could be like ground connection or 5-volt connection or reset line. Anything that is connected to each other is in the net. So like this would be one net, and this would be one net, and if these were if these are connected to the same thing, this would all be on one net. We'll show some on actual schematics too. Quick terminology review: a net is a point of connection and can connect to 2 or more pins. So like ground is a net, but also TX, RX, clock. So ground's connected to a lot of different things, but it's just one net. A symbol is a graphical representation of a component. So like this is the resistor symbol, which you've probably all seen before. And a designator is the letter and number referencing a single part. So R for resistor, C for capacitor, J for header, U for an IC. And so just some examples, this whole thing is a symbol right here. It's a symbol for a 6-pin header. This is a designator, P1. This is a net. This is a net, so VDD and ground will both be connected to a lot of things, but it's all just one net. MOSI is probably only connected to one other thing, but it's just one net. This is a ground symbol. Yeah, so those are just some examples of nets, symbols, and designators. So how are you going to organize your schematic? You can put it on multiple pages if it's a large schematic, like, you have a lot of different components and a lot of different connections. But a small, simple project like the one you guys will be doing soon can just be on one page, and for simplicity. If you have a larger project with multiple pages, do make a title page. It will define the intent of the board. It will give you a table of contents for the rest of the schematics, where to find things, etc. For instance, you could have like a page for your microcontroller, and a page for all of your headers, a page for all of your like a certain connection that you have, like maybe an LCD could have its own page. If you have components that are across pages that are connected to each other, you have to connect those nets across the page. You can either do this using off-sheet connectors, or you can adjust the settings so that nets just connect across pages in Altium specifically. Altium defaults to creating a room for each page, and we'll get into what that means, but essentially when you go into layout, it will try to group all of the components on a single page together. You can just disable that if you want to, but that's the default. You can also use something called hierarchical design, which I can never pronounce. Basically, this kind of creates like a block diagram of all the components in the system. So it looks something like this, and let's say you have this port IO, this schematic document, and you want to just copy it a bunch of times. You can just do it once and then make essentially a bunch of copies, and you won't have to make a bunch of different schematic sheets, and then you can organize it on your top sheet like this, connecting to whatever this controller is. Really helps to define cross-page connections, and it makes things a little more clear. And it'll show you like everything that's connected to one thing. So like you can see everything that 5 volts is connected to. You can see where this I2C goes, and you get like a nice block diagram. If it's not a hierarchical design, it's called flat design. Okay, so when you're making schematics, you want to make sure you read the data sheet for all the components that you're using. A few really important things, but definitely not all of the important things. Pin descriptions. So read the function associated with each pin. Pin 1 is reset. Don't just read like what it is, but how you need to use it. A lot of pins sometimes need to be connected to a capacitor or a pull-up or pull-down resistor. Make sure you read the complete description of the pin. It's not very long. It's going to be like a sentence or two. And it often links to longer descriptions later in the data sheet. So for instance, like the I2C lines will just say, do an I2C, have pull-ups, etc. But later on, it will tell you like exactly how to use those connections and how the I2C works in the component. There's an electrical characteristics section, which will have something called absolute max rating. So, what's the maximum current that you can draw? What's the maximum voltage you can put across this? Maximum temperatures, that kind of thing. And then it will also give you typical electrical characteristics. So what's the current draw at this voltage? What's, things like that. What's the resistance at this temperature? And then the layout for a pin. We talked about this earlier when we were going over component creation, but usually, it's at the end of the sheet, and you can use it for creating a model of a component. And this will give you like, measurements between pins and across components. If you have any off-sheet parts or connections on your schematics, so let's say you're plugging in a motor, you won't put the motor on your board, you'll put a header for the motor on your board. Don't just put a header and call it motor. That's not good enough. You need to like create a text box or something to explain what is being connected there, and give like a part number if you can, like, what's the part number of the motor you're connecting or the LCD you're connecting. This enables the next person looking at your schematic to understand, like, what is being connected here, what are the power constraints, the communication ports. Someone should be able to read your schematic and know exactly what's happening. Just give a little text box, explain what's happening, give part numbers, be as descriptive as possible as you can in your schematics. Right, test points. So these are designated, accessible, exposed points on the board connected to desired nets. You might have seen these 6 test points on the board and wondered what they were for. That's what those are. They're test points. They're very useful for debugging and prototyping. So let's say you have a multimeter and it's kind of, you don't really know exactly where ground is connected. Which pad should I connect? Oh, is it connected to this little half of this resistor? I don't know. But these are clearly labeled and you can see, okay, is my battery properly connected? Let's probe here and let's probe here, and we'll see how it's connected. These are also great for if you want to connect an oscilloscope. So if you want to like measure the waves coming across, like let's say you wanted to measure MESO and MOSI and you wanted to read that communication and use a logic analyzer and see what was actually being sent. You could do that with these exposed pins. And you can also make through-hole ones that look like this. This is just another example, and they're really nice because you can put these little hooks in them, and then you can connect leads directly to them in those little clips. If you've seen those, very useful. So this is just something you can put on your schematics if you are making a prototype for the first time and want easy debugging. Solder jumpers. So are you not exactly sure how to connect something, or not sure like what you want to be there? Do you want maybe a resistor but maybe not? You can use something called a jumper, and these can either be connected or not connected by default. So these are default connected and this is default not connected. But as you can see, it'd be really easy to just cut this trace with a knife, or put a little bit of solder on here and connect these pads. And because these are exposed, it makes it a lot easier to do something called rework on your board, so changing things after you've already manufactured the board. This is a really common thing with TX and RX and serial. I'm not sure how much you guys have worked with this, but sometimes it's unclear how exactly those are connected. Usually it's supposed to go, TX to the other RX and RX to the other TX, but sometimes if you have 2 devices that consider themselves controllers, like, you're talking between 2 microcontrollers, you can get kind of hairy and it's just not always clear. So that's an example of something I've used these jumpers before. Or maybe you'll put a 0 ohm resistor here and then and not populate it. And you can either connect or disconnect this with a resistor of whatever size you want to do in the future if you're not sure if you even need a resistor there. Okay, mounting holes. So mounting holes are exactly what they sound like. They're used to mount a board to a mechanical structure, like here, for instance. You want a case for your PCB. It's usually not just hanging out. You can use them to connect to standoffs. So you'd screw into standoffs to connect to some case. Sometimes you want to ground them if you want to connect them to ground, and that will just provide a wider ground plane if you're connecting it to a metal chassis, for instance. So sometimes it's just nice to ground your mounting holes, and then this is one example of that. You want to logically space these. This is more important for layout, but just space them in a logical way. Don't space them 36.76 millimeters apart. Do them 75 millimeters apart. Just space them logically, so mechanical design is easier if you're building a chassis. Keep things legible on your schematics. I see this kind of thing all the time, and these are some examples. So power is facing upward and ground is facing downward. Don't do this. This is confusing to look at. Ground goes down, power goes up. Other things usually go side to side. So these are some examples of what not to do, what you should be doing. If you have like a lot of nets, don't try to like wire them. Like, do you see how here it's really hard to tell, okay, where is this actually going? Well, if I trace it and here, okay, a little confusing. Now you have all these overlapping nets and you're trying to see, okay, is this connected here? Oh, no dot there. Okay, we're moving on. It's very difficult to see. So just make it like this instead. Just assign the net names, and then you say, okay, what's MESO connected to? MESO. Nice and easy. And it's not a mess to look at. This is painful. This hurts my eyes. Don't do this. If you have multiple I2C lines or serial lines, be specific. So don't call everything RX, TX, or don't call it like RX1, TX1. Call it like MCU RX or LCD RX, etc. Just name things. So it's a little easier to tell what we're talking about. Here there's only one SPI line, so you don't have to do that. But if you had multiple ones, you would want to call them clear things. More legibility things. When you have multiple overlapping lines, clearly show what is connected and what is not. So here, this could be like these two lines are connected, or it could be like these two lines are connected and these ones are not, etc. You can't really tell because they're all one dot. So if you just went like this, it's very clear, okay, these lines are all intentionally connected. So do that. Another thing I like to do is put boxes around like related groups of items. So I'll just literally just draw a text box and label it, and so you can just very clearly see, okay, these are the LEDs, these are the test points. Just kind of groups them together, because if these are just kind of scattered all over the schematic, it might be hard to tell if they were related. Okay, this is a very, very, very important. Pay attention to this slide. This is important. Decoupling capacitors. You will use these on every single board you make. So pay attention. We went over RC filters in an earlier lecture. If you don't remember that, go back and watch the common electrical components and concepts slide. It was one of the very first videos I released. But the idea of an RC filter is, well, in this case, the low-pass RC filter will filter out high-frequency noise and let through low-frequency. Let's say you have a signal coming in that looks like this. It's really messy. You filter it, and out comes a beautiful, nice, clean, low-frequency signal, which is, in this case, DC. This is going to be super useful for any of your like power lines. If your microcontroller has a messy power like this, then everything else is messy, because everything operates off of that voltage. All the transistors internal to this are going to be operating off of that, so it needs to be clean. Example with EMI, so electromagnetic interference. If you have like a spike on the voltage line, like these spikes, it will just clean it out really nicely. So it's super important. Really important for analog signals. So if you have if you're using an ADC on your microcontroller, super important that you do this. You'll probably have multiple filters, but typically you're just going to want to throw one on each voltage input. We use a 0.1 microfarad cap. You might be wondering why. That's just the standard that we're going to be using, because it's basically big enough where it filters out most of the messy noise you're going to need, but not too big where if you turn voltage high, that it's not going to take too long to rise. Because if you consider it a transformation like that, like if you turn a source on, that's basically just a big spike, because it's going from 0 to VDD really quickly. So if you flip a switch, it's going to create basically a high frequency signal, and that you don't want that to be really slow to rise if you have too big of a capacitor. So we use 0.1 microfarad capacitors. You'll see this on like literally every schematic you look at. You'll see 0.1 microfarad capacitors. That's why. And now we're going to walk through the schematic of the clock tower. I'm not going to do the whole thing for you because I want you guys to do this yourselves, but I'll walk through all the components that we're using and talk through some things that you need and how to generally do that in Altium. Okay, so we're going to go through some basics of how to make a schematic. For this project, you guys will be making the schematic of the clock tower board that I've given you. I intentionally did not give you a schematic for this board so that you could be making your own and not be just basing it off of the one that I shared with you. So we're going to start by just opening a new project. So File, New Project, and you're going to want to call this clock tower, and then your net ID. So mine is KB278. And you can save this wherever you'd like. I'm probably going to save mine here. And you can just create that. Okay, and now the first thing you're going to want to do is go to right-click on this and say Add Existing to Project. And I shared with you guys these libraries. So this is the PCB library and the schematic library, which is the footprints and the symbols for the components that you'll be using for this project. So you can add those to the project, and it'll fall under library. So you'll see the PCB library and the schematic library, and that will give you all the components that you need. Now you're going to want to copy and paste in the component that you made. So you guys made a Atmega 328P. You can just take that and you can just copy it from your other schematic library and just paste it in here, and then make sure you attach the footprint here. Do the same thing with the PCB library, and then you can attach the footprint. So that's how you're going to integrate that into this library that I've given you. Okay, so now that you have that, you're going to want to right-click on this and say Add New to Project, and you're going to add a schematic. You can save this as the same thing, clock tower KB278. You can name these all the same things because they're different kinds of documents. So you're gonna create this schematic document. Now that you have the schematic, you can start putting in parts. So if you press PP, it's place part, and it'll open up this components window. And you can go to the clock tower schematic library and PCB library. So you're going to open a schematic library, expand schematic. And you can start dragging in components. So the first thing you want to do is probably put in your Atmega 328P. The microcontroller for your project probably looks something like this. You're going to drag in, resistors and capacitors and set the schematic up. So that's how you get components into the schematic. Now, how are you going to want to go about doing this schematic? Well, yeah, the first thing you want to do is the microcontroller and make sure you have everything set up to run this. So you can also place power ports, which will be your VCC and ground. Remember, space shifts, space rotates thing. So this is by default going to place a power object. If you double click on it, you can actually change that to something like a ground. You can make it a ground. You could make it signal and power ground. And all those are fine. Bar is usually used for power, so that's what that would be. It would be VCC, and it's already called VCC, so that's what the name of your power port is called. You can name it something else. You can call it VDD. You can call it whatever you'd like. And then in order to connect these, you can press key W, and this will place a wire. And you want to go from the pin that you've made to that, and that connects this. This is connected to the pin of the power pin. You want to do the same thing for ground. Power port, place it, and if you double click on it, you can make it a ground and call this ground. Now we're going to want your ground facing down, so ground will look like that. And then we do PW again, and we get the ground. So that's how you're going to set up those kinds of things. If you want to place a net on something, so if you want to connect things to each other, you're going to want to place, I usually use off-sheet connectors just because they work across sheets. So you'll just place one like that. You can double click it and call it whatever you want. You can call it, LED 1, whatever you want to call it. And you can connect that to whatever pin you'd like. So make sure you read the data sheet for this. There's some pins that you should not use as input-output pins. For instance, if you use TXRX for this, it'll be very difficult to program it because typically I program these by just putting them onto an Arduino Uno and then program it from there. And TXRX is used to connect that Arduino Uno to a computer, so I wouldn't use the TXRX pins on this, for instance. The reset pin, so if you read the data sheet, you'll see that reset is active low. So you're going to want to use a pull-up resistor on reset. Make sure you add a pull-up resistor here, and then don't connect it to anything else. You have enough pins, you don't need to use that for other things. The crystal pins, that's going to be used for the clock. So if you read the data sheet, you'll see that this utilizes an external clock. So it doesn't matter what direction you connect it in, it's bidirectional, but make sure you connect that clock. And then you might see on the BOM, I had to use certain capacitors. Read the data sheet and see how those calculations came about. And if you're confused about that, do let me know. But there's a section on how to calculate what capacitors you would use for the crystal to connect to that. And I'll show you examples in the data sheet again of how to do that. So you'll connect everything to the microcontroller, and that's how you will do the schematic. You can make sure that the power pins have 0.1 microfarad capacitors on them. We talked about this a bit in the schematic, the first part of this video, the schematic overview. So you're going to want to make sure that you have 0.1 microfarad capacitors. They're also 100 nanofarad is the same thing as a 0.1 microfarad. And those just connect. Come on. Those connect to all of your VDD ports. Like so. So all of your power ports should have that. If you see like AVCC should have that as well. So yeah, so make sure those are connected to all of your power ports and connected to ground. And this is that low pass filter, that decoupling capacitor we talked about. All right, and then other things on the schematic. So you're going to want your buzzer, just like this, and your battery, and your LEDs, and your switch. Okay, so this buzzer can be connected on one side to the input from here. You want to put a resistor in line with that. If you just read a data sheet on piezos, like just put a resistor in series with this connection, such that it doesn't have too much power going through, and it can't like damage the microcontroller either. Just put a resistor in line with it. I chose a 1K resistor, and then connect it to power on the other side. So this will be driven by the microcontroller pins. The battery, I connected to this switch. So you connected to ground on one side, and then for the power, I connected it to the switch and said, okay, like if the switch is on, I want it to go to VDD, so I would connect it to this. And if it's not on, you can either just leave it floating or connect it to ground, anything you want. Doesn't matter. Just connect it to something that's not power, so that you can turn it on and off with the switch. So you'll connect it to these pins. The LEDs. So these are one of the components on the board that are directional. So it needs to you need to connect this so that power will flow through it. You also want to, you'll see on the board that I use 330 ohm resistors for that. I think you say 220, but yeah, you can use you can make them 330 just by changing like the value and the part number. So you can put those in line with the LEDs. Those in line with the LEDs. Drive these again from here, so you can connect this, to here. And you'll want to make sure that current is flowing from positive to negative. So you want to have ground connected, and you can, or you can do this one of two ways. You can either connect this to VDD on this side, and then have it flowing to a pin which will go high or low. You can connect it to ground or VDD, or the opposite way around. It doesn't actually matter. These can pull high or low. So do it either way you like. You can connect this directly to power or ground, but don't connect it to both, because then you need to be connected to the microcontroller on one side to control whether or not they're on or off. Okay, so I hope that makes sense. That's how you're going to place all of your components and how you're going to connect them. If you'd like to place test points, you can connect this to, say, like ground or VDD. And the way you do that is literally just by, it's only one pin. All it's going to do is just be exposed piece of copper that's connected to the pin, and that will just help you in debugging. So that's how you use test points. I would throw a couple of those on there. So if your board doesn't work, you can use your multimeter and find out why a little bit easier. Okay, so those are all the components you're going to want to have on your board and how you're going to want to connect them. Once you have them all connected, make sure you save this periodically, and you can go to Tools, Annotation, and Annotate Schematics quietly. This will assign the designator number. So if you see right now, everything just has test point, question mark, U, question mark, U, question mark, C, question mark. If you go ahead and annotate these, it will assign numbers to them. So now it says C1, R1, LED1, R2, and that's just differentiates between them. So when you make a part list, it will give you like, okay, all of like the BOM that I sent you guys. Okay, C1, C2 are these components, C3, C4 are these components, and it just differentiates between them. So this is just giving the numbers so you know which one is which, and that will assign numbers on the board that you can read and see what's going on and where you need to put things. And then one more thing you're going to want to do is all the pins that you're not using, you want to place these generic no ERCs. That basically means it's not connected to anything. So it'll tell your compiler there's nothing connected there. Don't just place it in the middle of nowhere. And that will just when someone else is looking at your schematic, you can see, okay, these pins are not supposed to be connected to anything. They're not just left hanging. They're intentionally not being used, and we just don't have to connect them to anything. Another thing I want to go over is you're going to have a lot of LEDs. You're going to have 12 LEDs with their 12 resistors. And so that will be, you can get kind of messy on this, if you have like a lot of things all over the place. So what you can do is you can place a text frame, and what that will do, you can label it if you want. You can say LEDs, and LEDs, that's what you want, and you can change it to be no fill color, and you can give it a thick border. I usually just make them red because I like that color. And you can make the text bigger if you want. Change the color of the text, whatever you'd like. And then you can just use this to encompass all of these. So yeah, you'll add like 12 of these, and you can put it all in a box and label them, and it just helps organize your sheet a little bit. The other thing is that when you're done, you can go to Project Validate, And what that will do is it will tell you if there's any problems. So obviously I have some problems because this is not a real schematic. So duplicate designators, LED question mark. I haven't assigned, I just copied and pasted these. And so again, they gave them the question mark and I didn't annotate them. So you'll need to annotate them and give them different numbers. Same thing with the net names, because these are, this is a net, and they're both the same thing. So they're going to be having the same net. And LED 1 is not connected to anything. So that's also a problem. I have it connected here, but I don't have it connected here. And that will tell you that. And yeah, just undesignated parts. So you can run this validation and see if you have any problems that Altium automatically picks up on. So again, project, validate, and that will tell you what kind of problems you have. It won't tell you all of your problems. It didn't tell you, okay, these pins are not connected, but it will give you an idea of, okay, I forgot to connect this LED, I forgot to annotate this, that kind of thing. Good. Yeah, so that's really it with the schematic. Obviously, you have to connect all of these things and create all the pins and read this data sheet and see what you need to connect to what. You don't need to read the entire data sheet. You just need to read enough that you know what all the pins do and what you have to connect to them. You will probably do something wrong the first time, and that's okay. I'm going to set up like design reviews with you guys and go through and explain what's wrong with them. Or I mean, you could do it perfectly the first time. I doubt it. That's okay. My schematics were not perfect. Still not perfect. We're not perfect the first time I made them. I have lots of room for change, so that's okay. We'll go through them and